Welcome to the debate.
It really is a profound moment in networking history, isn't it? The whole foundational concept of traffic steering, load balancing, is being completely reinvented by software.
It is, yeah. We're moving well beyond just, the simple idea of distributing bits across a couple of links. Load balancing today is absolutely critical for application scalability, for high availability, and performance. And increasingly, it's a frontline component for security and intelligent routing decisions.
And that pressure is immense, especially as applications just abandon static data centers and workloads migrate entirely to these cloud-native microservices and Kubernetes-centric architectures.
Which brings us right to our core question today. When we're designing these enterprise and service provider networks, should professionals prioritize the new, flexible, cloud-native load balancing solutions that are based on eBPF, Extended Berkeley Packet Filter? Or should we really rely on the deeply integrated, proven, traditional Cisco forwarding mechanisms and certified appliance solutions?
Well, I'm here to support the rapid adoption of the modern, pervasive eBPF-based model. It's really the only way to achieve true cross-platform consistency and the kind of agility that these modern cloud-native environments fundamentally require. It's a necessary architectural shift.
And I'll be arguing for stability, reliability, and reduced total cost of ownership, the TCO. These are factors that come from prioritizing the established Cisco forwarding mechanisms, whether that's integrated router software using iOS and CEF, or certified solutions running on the unified computing system. We really shouldn't trade decades of proven operational stability for just a promise of kernel agility.
I understand the appeal of the tried and true. I do. Traditional mechanisms are comfortable, right? They're comfortable because they're tied directly to the physical hardware and the infrastructure components that network teams have mastered over years.
Exactly. For decades, load balancing has been an inherent and essential function of Cisco router software. It's built directly into the forwarding process. This isn't some afterthought. This is maturity in practice. Just think about it. Router load balancing is automatically activated via standard routing protocols, RIP, EIGRP, OSPF. Whenever the routing table installs multiple equal-cost paths, we can reliably configure up to 6 of those paths today.
Okay, that certainly addresses Layer 3 path stability. But how does that address application layer performance, which is what the application teams actually care about?
Oh, it absolutely impacts performance and reliability in ways the application layer depends on. Fast switching enables this highly efficient per-destination load balancing. Now, this is crucial for preserving packet order within a single flow, which is a necessity for many applications and legacy protocols. The alternative, per-packet load balancing, it's just so processor-intensive and generally ill-suited for higher-speed interfaces, unless you have enormous dedicated processing power. And Cisco Express Forwarding, CEF, it accelerates both of these mechanisms, providing deterministic speed rooted right in the data plane.
Right. I'll acknowledge the deterministic efficacy of CEF for high-speed packet forwarding, but its philosophy is still constrained by the traditional network stack. It distributes flows based on layer 3 or 4 tuples. It has zero native context about the application running above it.
For the enterprise data center, the integration value of that existing path is enormous. You have established L4 to L7 solutions, like Edge Nexus, that are IVT certified for Cisco UCS B-Series and C-Series servers. You get a robust feature set, sure, but more importantly, you eliminate complexity. You are removing the need for a separate third-party external appliance, reducing complexity in the physical path, simplifying management, and fundamentally, lowering that TCO I mentioned. You buy a certified box, you turn it on, and it just works with guaranteed integration.
But that's such a hardware-centric viewpoint. The issue is that those traditional mechanisms, even when you successfully integrate them into a UCS rack, are inherently inadequate for the demands of modern, multi-environment, Kubernetes-centric applications. They just create operational silos.
And this is where you're going to present eBPF as the singular answer?
Precisely. We're talking about the new generation of solutions like the isovalent load balancer, which is built on open source eBPF technology. It's supported by key industry players. CNCF, Google, Meta, and it directly addresses this fragmentation of environments. It provides a consistent, high-performance load balancing layer that can run natively in Kubernetes and virtual machines and public cloud services, and it's architected to run on advanced smart switches like the Nexus N9300. That consistency is a key selling point here.
A single solution across everything is certainly an attractive operational goal, I'll give you that, but only if it can deliver the stability and security that's required. We are now relying on a programmable software abstraction layer operating deep inside the kernel.
And that is exactly where the superior functionality and agility come from. Because the mechanism is no longer confined to these low-level hardware constraints, it can provide granular L3 through L7 load balancing. We're not just matching IP and ports anymore, we're matching based on HTTP headers, cookies, URLs, or even custom application data. And crucially, this software model is self-healing, it supports auto-scaling natively, and it integrates fully with modern CI/CD practices. This drastically accelerates deployment and eliminates that slow, error-prone ticket ops configuration process that hamstrings application teams today.
So that moves us directly into the core tension, doesn't it? Deterministic forwarding versus kernel agility. From my perspective, while sheer speed is always important, the predictability of Cisco iOS and CEF is paramount for reliable networking.
Predictability in this context just sounds like an intellectual resistance to adopting new technologies.
Not at all. Stability matters when you're managing millions of flows. Load balancing decisions in the Cisco context are rooted in the calculated routing table or based on simple, known hashing mechanisms for aggregated links. This ensures packet order preservation and stability. Just consider link aggregation group, or LAG, load balancing on switches. It uses the reliable XOR method based on MAC or IPAC addresses to distribute traffic across aggregated links. It is a time-tested method for increasing bandwidth and redundancy at layers 2 and 3. You know exactly why a packet went down a specific link.
Okay, determinism is suitable for simple port aggregation, yes, but agility is foundational for infrastructure security and observability today. The eBPF model's programmability allows networking, security, and observability features to run securely in a sandbox right within the Linux kernel. And this is done without modifying kernel source code, which means no reboots, and critically, zero service disruption. That is a foundational architectural shift that hardware appliances just cannot match.
What is the tangible operational benefit of that shift, though, beyond just faster deployment?
It enables highly dynamic compensating controls. Okay, so if a new zero-day vulnerability, a CVE, is announced, eBPF allows network engineers to deploy a live protect security policy, which acts like a micro WAF or an immediate filtering mechanism. It can be deployed in minutes across your entire fleet, kernel side, without ever touching the application or rebooting. How quickly can a network engineer deploy an emergency firmware patch across 100 hardware appliances?
That is a compelling argument for rapid response, but it shifts complexity into a zone that is notoriously difficult to monitor and debug, the kernel itself. Traditional network teams are experts in iOS debugging, show interface, show running config, not tracing BPF programs. Who is going to own the operational fallout when an eBPF program misbehaves and crashes a VM?
See, that fear is based on the legacy model of kernel modification. eBPF is designed for safety. But to address your point about observability, the system is actually superior for monitoring. eBPF becomes a highly efficient and optimized data collection mechanism for tools like Splunk because it intercepts network data before it gets to the traditional kernel stack. This gives us richer context and lower overhead than traditional sampling methods like NetFlow or IPFX, which really optimizes the signal-to-noise ratio. I mean, we are processing 10 million packets per second per Intel core. That performance scale aligns perfectly with hyperscale cloud requirements.
That speed is impressive, but let's circle back to the established deterministic mechanisms. They still demand extremely careful, expert configuration to avoid major operational pitfalls, which to me suggests that the required complexity is simply being shifted, not removed, when moving to software. Take the lag example I mentioned. Practitioners have to be vigilant. With a 2-port lag, using the IPA MAC algorithm can sometimes result in suboptimal balancing, where all the traffic utilizes only one port, because the XOR calculation returns the same value for every flow. This often forces reliance on the simpler, less granular mode, just to achieve better link utilization.
And that is exactly the problem. That low-level reliance on understanding the intricacies of hashing algorithms just to achieve basic link utilization is operational friction. We need to eliminate this deep, low-level configuration required for traditional mechanisms because it demonstrates their inherent limitations in advanced network fabrics.
Can you provide a more robust example of what you're calling operational friction in a modern fabric environment?
Absolutely. Let's look at deploying traditional appliance-based load balancers in a Cisco ACI environment. ACI uses IP data plane learning, which, by default, creates significant problems for seamless failover and for direct server return, or DSR, functionality.
A well-known quirk of ACI's endpoint mapping. Yes.
It's more than a quirk, it's a roadblock. If the load balancer fails over, the ACI fabric often incorrectly relearns a virtual IP on the wrong endpoint. Or in the case of DSR, the fabric may bypass the load balancer entirely and send all returning server traffic to a single host. Overcoming this requires non-default, manual, and often bureaucratic configuration steps. You have to explicitly configure the VIP as an L4 to L7 virtual IP and enable GARP-based EP move detection within the bridge domain's L3 configuration. This is why application teams have to file tickets that wait for days just to get a load balancing service deployed. The underlying physical fabric clashes with the application requirement.
I would argue, though, that those configuration challenges are inherent to specific, complex fabric architectures like ACI, not a flaw in the underlying load balancing concept. The concept itself has proven flexible enough for decades. The complexity comes from the interaction of multiple control planes. For routing, we have long managed unequal cost path load balancing using the variance command in EIGRP and IGRP. That command is an explicit tool to maximize link utilization based on costs and metrics. Does managing the variance knob in EIGRP make EIGRP a flawed protocol? No, it means it requires expertise to maximize its potential. The same applies to ACI integration. It requires expertise in managing that control plane interaction.
But expertise should be spent innovating, not filing tickets to manually override the default ACI learning behavior. The isovalent approach, it seeks to remove that low-level configuration friction entirely by providing a consistent deployment model across all environments, VMs, cloud, Kubernetes. This vision aims to make the new load balancer the, quote, nexus of cloud native, offering centralized, highly advanced L7 features, web application firewall, global server load balancing, bot management, capabilities that legacy IS forwarding simply cannot natively match or integrate universally.
Wait a minute. While eBPF offers deployment agility, the integrated appliance model offers significant advantages for centralized management, auditing, and compliance. If you decentralize your WAF and your GSLB into every single kernel, where is your single point of operational policy and auditability? Certified appliances, particularly those running on UCS, provide a consolidated point for security logging, for configuration rollback, and for regulatory scrutiny. You sacrifice centralized auditable control for decentralized agility. That's a massive trade-off.
That auditability is now provided by the control plane managing the eBPF layer, not the hardware itself. You can audit the policy configuration applied via Kubernetes manifest or CI/CD pipelines far easier than auditing 100 different appliance configurations. Apply these different CLIs over a year. And furthermore, the L7 features you mentioned, like GSLB and WAF, are features of application delivery controllers, which is precisely what eBPF is enabling in software without the vendor lock-in or the licensing complexity of traditional appliance vendors. We are shifting the control from a physical choke point to a pervasive software layer.
So we agree that high-performance, complex application delivery remains essential, but we disagree profoundly on the best locus for that control, whether it's integrated into the stable, deterministic forwarding plane or delivered as a flexible, software-defined kernel layer that promises agility but introduces new debugging and control challenges.
Exactly. It's a debate over stability versus velocity.
To summarize my position, Cisco's established methods provide essential, predictable, and highly accelerated traffic distribution through CEF and routing protocols. The stability,
the performance, and the operational simplicity of integrated iOS features remain foundational to predictable network operations, especially when paired with reliable certified deployment via solutions like EdgeNexus on UCS. This reliance on established mechanisms maximizes performance and minimizes TCO where it matters most, in the core, stable forwarding path.
And my position remains that the infrastructure future demands unparalleled agility and consistency across hybrid and cloud-native environments. The foundational shift toward eBPF technology, championed by modern solutions, offers superior flexibility, granular L3 to L7 control, and a critical alignment with modern DevOps workflows. It actively resolves the inherent operational complexities and configuration friction introduced by trying to integrate legacy infrastructure into modern application delivery.
Well, regardless of which path one takes, the hardened integrated approach or the agile kernel-level software approach, our discussion confirms one thing. Load balancing, whether it's handled by routing processes, aggregated links, or dedicated software, requires continuous, highly nuanced expertise.
Absolutely. The core principles of reliability, performance, and flexibility remain paramount to successful infrastructure design, which confirms that there is still a great deal to explore in how these new, powerful technologies are ultimately deployed in production environments.
Indeed. Thank you for this enlightening debate.
A pleasure as always.